All right. On this glorious day of school, we're going to learn about wave speed. You ready? Make a lot of noise. It seems like a lot of people here. Yay! Yeah, you got to watch this video and learn this, you bums. All right, wave speed. What's the symbol? Don't all jump at once. It's the speed. V. You know what speed is. Anyway, there's a three-word definition we can use for wave speed. It's the very first equation you learned. Do you remember it on PRT 6, the very first equation? Yeah, so your three-word definition right here is distance per time. Just conveniently goes with frequency, period, and wavelength. Remember those three? Frequency, what is it? Cycles per time, right? Period. Time per cycle. Wavelength. Distance per cycle. And finally, speed. Distance per time. So you need those three-word definitions. They're very useful. Okay. Wave speed depends only on the medium. If the medium changes, the wave speed through the medium changes. Right now, this doesn't seem like much, but this is going to be a heavy concept throughout waves. Now this phrase over here, particular medium, is kind of like neglect friction from when we did kinematics, when we did projectiles. When you saw neglect friction, you always knew you could use that acceleration of 9.81. Here, in your wave problems, if you see particular medium, you will know for certain that the wave speed is constant. So that's what that phrase is going to give away. This seems like the sort of phrase you can ignore. It's not. It means the wave speed is constant. And wave speed being constant is very useful because then you can pop it into the equations, which assume a constant wave speed. So here are the two possible equations. The equation from PRT 6, V equals D over T. That's really a average speed, but it works nicely with constant speeds. The unit there, of course, is the meter per second. And we have another equation for wave speed, which we'll try out today. It's on PRT 6, 5, not 6, 5. What's it say? Yeah, V equals lambda. V equals F times lambda. Frequency times lambda. There it is. What's the unit going to be based on that one? Typically we stick with meter per second. But if you wanted to, what could you call it? A hertz meter. That's right. Frequency is hertz. Wavelength is meter. So you could have a hertz meter. That's also a fair unit for wave speed. So now let's make use of this particular medium business up here. If a wave is propagating, traveling, transmitting through a particular medium, there's that phrase, particular medium. What's that mean? Yeah. Particular medium, since wave speed is constant, then, well, we have an equation. This asks us how frequency and wavelength respond to this. Well, if you look at the equation, V equals frequency times wavelength, if you're in a particular medium, this wave speed has to stay the same. If the frequency goes up, what has to happen to the wavelength? There it is. It has to go down to balance it out. That wavelength will have to decrease. Of course, you have the same down here. V equals frequency times wavelength. If you're in a particular medium, speed stays the same. If the wavelength goes up, the frequency then will decrease. What does the shape of this graph look like? Well, it's not a guess. Make this the y. Make this the x. Your equation, v equals frequency times wavelength. Rewrite it. How are you going to rewrite it? Kiva, what's yours say?
Like the wavelength equals frequency. Wait, no.
Just put in the letters and the ones. Make that easy. We'll rearrange after.
Oh, 1 equals x times y.
Yeah, 1 equals x times y. Now some of you already know what that is, but just in case, you can't plug it into your calculator unless it's in y equals. So divide both sides by x. And y equals 1 over x. Put it in your calculator, what does it come out to? Yeah, the inverse graph, the water slide. It's not a straight downhill, it's this one. A warning, not that you probably need it because nobody seems to like Dr. Sarf anyway. But if you are multiplying the coordinates here, frequency times wavelength, you can pick a singular point, any singular point along this curve. Like here, or here, or here, or here. This has a particular frequency with a particular wavelength. So does this one. So does this one. That product will always equal the wave speed. So if you're ever given a graph and they say, what's the wave speed? Find one point, multiply the coordinates, done. The reason you're not actually doing area here is because there's nothing about frequency that accumulates. Normally when we do like a force versus displacement, you do the area to get the work. That's because displacement or distance accumulates. There's no accumulation here. Alright, so let's do this real quick. From example 8, if each wave is 2 meters, so what's that mean? What given is this? Each wave is 2 meters. What would you write down as a given? Yeah, wavelength equals 2 meters. They say determine the wave speed. And then example 8, you have to flip back and find it. Which was example 8? Anybody have it there in front of them? What page it was? Well, that might have been. Oh, not there. Is it page 11? Yeah. Oh, all right, the one that we did the big drawing. There it is. So what do we need from this page, from example 8? What do we need that we don't have? Frequency. So jump over, back to page 15. They told us the frequency was 0.5, half hertz. And so to set up your work, to show your work on one of these is very easy. Wavelength, speed, frequency. You need an equation. V equals frequency times wavelength. Plug it in. V equals 0.5 times 2. And there it is. The wave speed is 1 meter per second, or 1 hertz meter. Get in here. There's a video going, so go sit down over there.
Just ran up here.
Good.
Where's Sam?
Shh, there's a video going. Sit down over there. Call him. Don't hit the table. Sit next to Bobo.
He's next to Bobo.
There you go. See, we got 1. We need more. We need more.
I was playing the cover and I fell asleep through my alarm.
You actually do look like you fixed your hair and then fell asleep. Because you got nice hair but sleepy eyes.
I did.
Alright, this same one over here, from example 11, if each wave has a frequency of 2 hertz, example 11, go check. I'm sure they gave us the wavelength in example 11. What was it?
4 meters.
How much?
4 meters.
4 meters, thank you. And so then, V equals frequency times wavelength. Frequency of 2, 4, 8 meters per second, or 8 hertz meters, either way. Now there is a little memorize bar down here. Where would you expect light to go faster? Well, I'll give you a hint. Light actually is a disturbance or a wave in the electromagnetic field. Do you need matter or mass in order to have the electromagnetic field? No, it exists in space. And so, effectively, when you put matter in the way, when you put material medium, when you put water or air or glass in the way, what do you think it does to the speed of light? It slows it down, it does. In fact, light goes faster in a thinner material. The thinnest of all being the vacuum of space. It actually is through the electromagnetic field. So light goes faster with less material. Sound is a wave through mass itself. Sound is a mechanical wave. Sound actually is like the domino effect, where one shaking molecule or particle or atom bumps the next, which bumps the next, which bumps the next. What do you think sound would travel faster? In a low or a thin or a thick material? And people might say a thin material, but a thin material tends to wobble. A thicker or more dense material, very rigid, that wave travels pretty rapidly. The domino effect is very rapid. Any of you ever set up dominoes? If you set up dominoes, do you know which way they knock down quicker? If you set them close to each other or if you set them far apart? Try it. Try it, and you'll probably find the same answer. Sound goes faster in thicker material. Sound is actually faster in water. Sound is faster through earth. And believe I told you about you can put your ear on the train track. Did I tell you that?
Yeah.
Don't actually do it. But if you were, you'd be able to, you could put your ear in, well, what if you could do it in the hallway? It's too far away. But you could hear warring tribes coming. Go outside and have your friends who are 50 miles away ride a team of horses towards your house. Put your ear to the ground, see if you hear them. Matt, you can set that up?
Yeah, definitely.
Good, good. All right. Let's do a couple practice over here.
Yes.
Hello, Mr. Ross. You look very strong.
You, 2, 4, 6, 7.
Let me stop this.